everyone, welcome to this video. In this video we shall be looking at the question from June 2018 consisting of 4.75 marks. The question is, the values of lambda for which the following equation has a non-trivial solution. This is the given equation where the kernel is given to be of this kind, right? So what is the value of lambda for this integral equation, whether it is A, B, C or D? So I suggest you to stop this video over here, pause it and try to solve it yourself and then proceed, play it again, right? So I hope you have done it, right? So let us see the question. The integral equation is given to be phi of x is equal to lambda integration from 0 to pi kxt phi t dt. So the interval is given to us 0 to pi, right? And this is a homogeneous integral equation, right, of the second kind. So let us solve this. So the kernel is given to us whose value is given in the interval 0 to t and t to x. So let's break our interval 0 to pi into 0 to x and then x to pi. So in the interval 0 to x, the integral is being taken over the variable t. So here t is strictly less than or equal to x, right? And here t is less than equal to x. So we'll take this value over here. So it becomes lambda integration from 0 to x cos x sin t phi t dt. Similarly here t is greater than equal to x, right? So here we'll take this value of the kernel. So it will be sin x cos t phi t dt. So now we shall solve it by differentiating it. That is, we are converting the given integral equation into the corresponding differential equation, right? So let us differentiate the given equation. So left hand side phi x would become phi dash x, and in the right hand side we have to take the derivative of the integration term. So for that we shall use the Leibniz rule. What is that? It is integration partial derivative of the inner term, right, and then plus the derivative of the upper limit bx and substituting t as the upper limit into the rest of the term minus the derivative of the lower limit with respect to x and substituting in place of t the lower limit, right? So let us look at the first term on the right hand side. So lambda as it is, integration from 0 to x. Then we take the partial derivative of this term with respect to x. It would be the derivative of cos x, that would be minus sin x, sin t as it is, phi t as it is, right? Plus lambda as it is. Then the derivative of x with respect to x, that is 1. And then we'll replace this t by x, the upper limit. So it will be lambda cos x sin x phi x minus the lower limit is a constant. So derivative of constant is 0. So the last term is simply 0. And the similarly we shall do with this term also. So lambda integration from x to pi, the partial derivative of this term with respect to x, it would be cos x cos t phi t dt. This remains as such because it is independent of x and we are taking the partial derivative. Then the the complete derivative of the upper limit, that is pi with respect to x, that would be 0, right? So this whole term is 0. And then the complete derivative of the lower limit, that is x with respect to x, so that would be 1. Lambda is this one. So lambda into 1 into this whole term where we replace t with the lower limit x. So it would be this. So now you see this term is same as this term. So we just cancel out these two terms and we are left with these two terms. So let us see. So these are the terms, right? So because we have the integral sign as such, so we differentiate once again. So differentiating, we get phi double dash x, and here we will again apply the Leibniz rule. So we get this term and this term, the last term is 0 because the lower limit is 0, and the second term this, and because the upper limit is constant, so this is 0 and this, right? So there is no problem, you can do it using the same Leibniz rule. So now this term cancels with this term. No, it doesn't. In fact, what you see, you have minus lambda and phi x common, so you have sine square x plus cos square x. So that is 1. So simply we are left with this term, taking common minus lambda and phi x from these two terms, and from these two terms it will be minus lambda integration of this whole thing. And in the question, if you see what is this whole thing, let us move back and you'll realize that this is nothing but phi of x. So let us substitute it over here. So what do we have? We have phi double dash x as this thing, minus lambda phi of x, right? No, lambda is also consumed. So minus phi of x minus lambda phi of x, or ultimately this is our equation, second order differential equation. So now to solve this equation, we also need some boundary condition. So let us look at the value of phi at the left boundary, that is 0. And we shall also look the value of either phi or phi dash at the right boundary. So let us look at phi of 0. So phi of 0, what would be that? From here you can see that if you put x is equal to 0, so this first integral is from 0 to 0, it becomes 0. And the second integral 0 to pi sine of 0, and sine 0 is 0, so this integral is also 0. So we have phi of 0 is equal to 0. This condition is true, right? We need another condition, phi at pi. What would be that? Here if you substitute x as pi, so you will have 0 to pi cos of pi, and cos pi is minus 1, so sin t minus phi t, and here this term would be 0, so you will have some non-zero term containing this phi t. So you do not have any constant value for this term, so this term we cannot find, right? So can we try for this term, phi dash of pi? What would be that? So let us look at this. We have phi dash is this term, right? So what would be phi dash of pi? So it would be minus lambda integration from 0 to pi sine pi, right? And what is sine pi? Sine pi, sine t, phi t. Sine pi is 0, so this whole term is 0. Moreover, here we are taking integration from x to pi, so it will become integration from pi to pi, and that would also be 0. So this term is 0. Phi dash of pi, that is 0. So we have the boundary conditions with us. These are the conditions, and this equation could be written as, the auxiliary equation corresponding to this differential equation could be written as d square plus 1 plus lambda, where what is this d? D is the partial the derivative of phi with respect to x, right? So here, depending on the value of this lambda, we have different solutions phi x. So let us see what if lambda is 0, what if lambda is positive, what if lambda is negative. When lambda is 0, we have our auxiliary equation becomes lambda is 0, so it becomes d square plus 1, that is d is equal to plus minus iota. So in that case, we have c1 cos x plus c2 sin x. So we put the boundary conditions, phi of 0, 0. So this gives c1 0, and we calculate the phi dash of x. Why that is required? Because for using the second condition, we must calculate what is phi dash x. So this is this, right? So calculating this, you again get c2 is equal to 0. So we have phi x is equal to 0, which is the trivial solution, and it is not required. So let us see the second case here. The value of lambda is k square. We are taking it to be positive, where k should not be 0. If k is 0, we again reach at this first case, right? So lambda is k square, so our auxiliary equation is this, right? We can solve this. We can move this part to the right, and then we can take square root on both sides. So we have something like this. So corresponding to this value of d, the phi of x could be written as this, right? So let us calculate its derivative also. So it would be the derivative. Now using the boundary conditions, phi of 0 gives us, just a second, phi of 0 gives us c1 is equal to 0, and phi dash of pi is equal to 0. This gives us this expression, right? So now either c2 is 0, but if we take c2 0, we'll reach at trivial solution, so we do not require. So we are assuming c2 is non-zero, right? Then because k is positive, so this whole term cannot be 0, right? This must be some positive quantity. So we are left only with this term as 0, equal to 0. So now when is cos 0? The cos is 0 at the values pi by 2, 3 pi by 2 and so on, like this, plus minus. So it could be generalized into this form, n plus half pi, right? Where what is n? N is plus minus 1, plus minus 2 and so on. So equating these, we get this. So from here we can calculate what is k or what is lambda, right? So our lambda ultimately is this. So basically in the question they were asking what is the value of lambda or the eigenvalue. So this is the value of lambda, where this n is some natural number. So we are done with this question. So our answer, let us look at the options. So option A is the correct option. Let us see the third case also, and for the sake of completeness, let us see what is the solution for this equation. The solution would be phi of x would be c2, where c2 would be arbitrary 1 plus k square square root cos of 1 plus k square square root into x. And what was this term? We calculated this to be n plus half whole square. So this is this, right? Square root of this is simply this term, right? So this is our eigen function if we require. And in the third case, let us also discuss that. So the third case, we have lambda is equal to minus k square, which is negative. So when you solve this, you will get something of this kind. And when you substitute the boundary conditions into this, you will see we again get the trivial solution. So the only non-trivial solution obtained in this case is when lambda is k square, that is positive. So I hope you understood this question. Thank you for watching.